Hello and welcome to session 5. In this one we're going to be looking at the weather. Right, so big weather to start with. We just need to understand the basic principles. So you may well be familiar with some of this, but we'll be referring back to it in future sessions. So it all starts with energy from the sun. Huge amount of radiation, various wavelengths being emitted from our star, obviously, which all come flooding down towards the Earth, so not to scale. When it reaches the Earth, we have differential heating of the globe. This is for various reasons, not least because the globe is spherical and therefore the sun strikes at different angles. It is actually not quite vertical, it's slightly tilted as well, as you're probably aware. And the other thing is there's a shell of atmosphere around it. And therefore, if the radiation from the sun strikes at a shallow angle, it has to go through more atmosphere, which reflect or absorb some of that radiation. The bottom line is there's different amounts of heat that arrive at the surface. This is exacerbated by the fact that the poles are generally white, so they reflect a lot of the sun's radiation as well. So we have this situation where less energy reaches some parts of the surface than others. We're all aware of the fact that when the sun is high in the sky, and therefore it's coming directly through a shallower envelope of atmosphere, if you like, there's a lot more energy there. But if it's very low in the sky, so late in the day or at high latitudes, sufficient less energy is there. Okay, so we get this differential solar heating. You see this is just a shot that I found on the internet just showing the differential heating of the globe. Of course, this is a very complex situation because the Earth is, of course, spinning and therefore half of it is in shade at any one time and not receiving any energy. Okay, so staying with the basic model, what we actually have then is energy from the sun heats the surface to whatever degree. When you heat air that is lying on the surface, what actually happens is the radiation from the sun is the wrong kind of wavelength to heat air. So what it does is it heats the surface and then the surface heats the air lying on it. So the atmosphere warms from the ground up. That conductive energy warms up a patch of air or an air mass, if you like, and that gradually expands. As you heat something up, heat up a gas, the molecules get more agitated, they bang off each other harder, and they basically spread out, and the density becomes less. So in other words, it becomes lighter. So warm air, as we all know, has a number of properties, but one of the ones that it does is as it becomes less dense, it becomes lighter and it starts to rise. So where we get heating on the surface, the pressure gradually reduces and the air starts to rise. So we get rising air. As it moves away from the source of the conductive heat, obviously it begins to cool down as it moves up higher in the atmosphere. And eventually, as the air cools, it starts to sink down again. So we get to sinking areas of air at higher pressure. So this is the basic cellular formation of air, warming, going up, drifting and sinking down again. And it happens throughout the surface of the Earth. So this is just a very simple model. There's actually a number of cells that we can actually track and plot over the surface of the Earth. So high pressure and low pressure areas, basically. Okay, we add to that then the fact that the Earth is spinning. There's the rotation of the Earth, and we get where the air is going up and sinking down again. Not only do we get airflows, but we get them curved. I've shown on this very simple model that them just being in straight lines and showing them slightly moving off to one side because of the spin of the Earth. However, they actually travel in a slightly curved path. And then further up we get, in the other part of the cell system, if you see what I mean, we also get predictable airflows, the trade winds and the prevailing westerlies. So this has been known to people for thousands of years. Obviously we used them when we were sailing ship, was the main way of getting around. Okay, so that's the big picture. Very, very simple model, but just to give you an idea. So now I'm going to look at weather forecasts, because obviously it's crucial to us as pilots, where we get our weather forecast from, how accurate it is, and whether we decide if it's flyable weather or not. So weather forecasts start out looking out the window, obviously. Either it's a nice day, like today, or it's not. If it's wet and windy or whatever, then, you know, that's the end of it. However, assuming that it looks like it might be a flyable day, or you're expecting tomorrow to be a flyable day, the next thing is to get a forecast. So we can get a basic idea from the internet forecasts or from the TV. These tend to be good for general weather and the trends. You know, it'll be a nice day tomorrow, it'll be lightish winds and what have you, and how it's going to be over the next few days. But they do have some drawbacks as well. They can't actually tell us about winds at altitude or the convection as a rule. So for those, we need these specialists forecasts. So I'm going to talk in a moment about specialist forecasts, or in a separate session that's entirely devoted to those, to RASP and aviation forecasts and so forth. But for the moment, that's the order that we look at. And then fourth, of course, you've got actual weather. So this is webcams, or frankly, usually the first guy out on the site, if you're on Telegram or something like that, will actually say to his mates, okay, yeah, it's looking good here at the moment. So different methods of deciding whether it's suitable to go flying. That's the order, really. Right, looking at weather forecasts, the main feature and the main way that all these forecasts are produced is working from a surface pressure chart. So it's worth us knowing a little bit about the main features of a surface pressure chart. Surface pressure chart is exactly what it says. It's basically a map of what the pressure is at the surface, and for the reasons we already discussed earlier, that has a big effect on the weather that we're going to encounter. So the pressure is measured in hectopascals. So the standard atmosphere is 1013.2 hectopascals. So this is par, if you like. A low pressure area, anything much below 1000 is a low pressure area, say 980, 990, something like that. And a high pressure area is anything much above that. So 1030, I've chosen an example here, is a high pressure area. And they are marked on this chart with an H and an L or whatever. And the little lines that join the areas of equal pressure, sort of pressure contours, if you like, are isobars. I'm going to look at those next. So here's your surface pressure chart with your various features on it. So high and low pressure, we've discussed isobars. Isobars are the thin black lines, and they are in hectopascals, and they're 4 hectopascals apart, which I'll talk about the value of that in a little while. We also have fronts that are marked on here. The fronts mark the interfaces between one air mass and another air mass, usually a warmer and a cooler air mass, or a damper and a drier air mass. And so they're quite interesting to us, because where those air masses touch, that's where we get our principal weather in terms of winds changing and precipitation and so forth. Static or waving fronts, I'll talk about those. And troughs, which is just a little sort of valley of low pressure without forming a full depression. So just to go through those, we've already talked about high and low, but isobars here. So these are the pressure contours of the map. As mentioned, they're about 4 hectopascals apart. That's the standard on a surface pressure or a synoptic chart. What does that mean? Well, it essentially means that by the width that the spacing between the isobars tell you how steep the pressure gradient is. So in other words, if they're a long way apart, that means, if you like, in a high pressure, you've got quite a shallow high, but if in a depression where they're very close together, sort of a storm, it's very deep. So the weather is going to be more exaggerated, or the characteristics of a low pressure will be more exaggerated. Okay, so there we are, steeper the pressure gradient. So this is a light wind day. We know this without even seeing any kind of wind arrows or anything, because there's only 2 isobars crossing the UK. So pretty light winds. If we get isobars closer together like this, packed, then there's a steep pressure gradient and we'll get stronger winds. As a matter of fact, as a rule of thumb, if you are a paraglider pilot watching this, then the height of the UK from sort of northern Scotland to the south coast, if there's 4 or more isobars crossing the UK, it's probably going to be too windy. Obviously not quite as simple to get 3 up north and 1 down south, then it's that spacing that matters where you are. But that's kind of 150 miles apart for 4 hectopascals. A hectopascal is worth about 30 feet in terms of pressure. It's the value of, so it's 120 feet difference in terms of altitude in those times. So it just gives you its way of visualizing how strong the wind is going to be. So anyway, packed, you already know this, strong wind. So high pressure system is where the air, as we mentioned already, is fundamentally sinking. So where it's sinking, what effect does that have on us? Well, it means we're going to have stable conditions effectively, because we're not going to get very much convection. Thermals and stuff can't go up particularly well because the air is sinking. And in fact, we often get temperature inversions because the air is sinking. It's actually beginning to warm again as it comes down and is being compressed. It's a bit like pumping a bicycle. As you take a big area of air and you squash it into a smaller space, it actually gets warmer as it sinks back down towards the surface. So we do get temperature inversions, which I will touch on in just a moment. Basically, good smooth flying conditions, so okay for ridge lift, great for paramotoring, things like that, but not much good for cross-country flying. You often get fog and mist in the winter as well in high pressures. They are sinking and warming inversions, restricted convection, lower pressure gradient, clockwise airflow. Right, when you're in a high pressure, the wind travels clockwise around the high. So little map here showing it. Now this is showing here the 2,000 foot wind. So we call that the geostrophic wind. The winds at 2,000 feet tend to flow around, they follow the isobars basically, so they go round a high or round a low. When you get close to the surface, then the wind changes slightly. So a surface wind, just look at this, on a high they tend to spill out slightly. So imagine on a high, imagine it going downhill. What's actually happening is you've got a pressure gradient wind and you've got a Coriolis effect of the Earth spinning, and the two sort of compete against each other. So high up, when you're way up, well away from the surface of the Earth, we just stick with it going right round following the isobars. But down at the surface, you get this spilling effect, so that the high pressure winds at surface level spill slightly outwards. Well, why do you need to know that? Well, clearly because if you are on the surface and the wind is in a certain direction, as you go up, it's going to change. So a couple of thousand feet could be 30 or more degrees different. Okay, so that's the way round, clockwise round a high, simple as that. This is in the northern hemisphere, I hasten to add, different in the southern hemisphere. So low pressure systems now. A low pressure or a depression, increased convection and cloud formation because it's easy for it to do so. More chance of rain, so we tend to get more cloud and rain, particularly around the frontal zones. As mentioned earlier, the isobars can be close together and therefore higher winds are more likely in low pressures. And we get an anti-clockwise flow. So a little diagram here. Again, this is the 2,000 foot wind and round a low. There we've got that anti-clockwise flow. And the same thing happens if you get down to surface level, we get a deflection. But with a low, it's not out, it's inward. So at surface level, you actually get if you imagine water going down a plug hole, so it's actually deflected inwards and pours slightly into the centre. It's the easiest way to remember it. Okay, so that's the characteristics of a low pressure. Okay, deflect inwards. Right, weather fronts. These are the standard notification of the front. So these are in colour. Sometimes you'll see them on a black and white chart, but they're shaped so that you can easily tell the difference between the different kinds of fronts. And on this one, I've got an arrow here just showing the direction of front. So if the little semicircle or the triangles, icicles, if you like, are pointing in one direction, that is the direction of the front. So you see the third one down there is a stationary front. It's got warm air on one side or cooler air on the other, but it's not going anywhere, so there's no movement. The bottom one, an occluded front, is where you've got warm and cool air, and I'll look at that in just a moment, but that is still moving. Okay, so here's a warm front. A warm front is essentially where a warm air mass is moving. Now, warm air masses have a number of characteristics. The two that we're interested in is that they are lower density, and the other one is that they absorb, or they hold, warm air holds much more water vapor, which as a gas, so it's much more moist air. So there's the warm air mass. As it hits a cooler air mass, because it's lighter, it slides up over it, and so as it moves that way, the warm air is moved up. As it moves away from the surface, we already established it cools down, and as it cools down, it's unable to hold the water vapor, and that coalesces out into water droplets as cloud, and then we get rain. So I'm going to look at this in a slightly odd way. Rather than that, I'm going to look at it as starting as if the front is coming towards you. If you start over at one side and the front towards you. So the first thing you see is high wispy clouds, cirrus clouds usually. They're at a high level. Up there, where the warm air is up high, it hasn't got very much moisture left, so it tends to be quite, thin cloud really. But as the front approaches and the warmer air is a lower altitude, you get thicker and thicker clouds. So you tend to get stratocumulus or just stratus clouds. There are various forms of cloud, doesn't matter about the names, but basically on a warm front they're all stratiform clouds. That is to say, they tend to be layers, fairly flat layers. Not always, but that is the general nature of clouds on a warm front. So the cloud base lowers as it comes towards you. It may start to drizzle if you get down low enough moisture in the air, and then as the front gets even lower and even closer, that drizzle will turn to more continuous rain. Eventually, as the front goes overhead, two things happen. You'll feel the temperature increase, well, unless you're soaking wet, which is quite likely. And the second thing that you will notice is that the wind will change slightly and the wind veers. So another technical term, wind moves in two ways, clockwise or anti-clockwise, and that is veering or backing. So back round the clock is the easiest way to think about it. But this is veering. So as soon as the front goes overhead, the wind will veer a few degrees. So those are characteristics of a warm front. The whole area that's affected by a warm front is pretty wide. It can be 150 miles wide. So if it starts to get wispy cirrus, and then the cloud lowers and it starts to drizzle, then you probably had it for several hours, because it's going to take quite a few hours for it to go across. So that's the end of flying for the day. It's quite common to see cirrus clouds late at night and then wake up to find it's raining the next day as a warm front is going through. Okay, so there's the warm front notification there. A bit of information. Okay, a cold front. Cold front. The actual mechanism is very similar, but what happens here is you have the cold air moving, so it kind of shovels up the warm air in front of it. So this is why I talked about being an observer on the ground. So if you're an observer on the ground, it's the opposite way around. The first thing you see is the low-level cloud with rain associated with it. So if it's an active cold front and it's pushing up the warm moist air quite quickly, you can get really big clouds. On an active cold front you might get cumulonimbus clouds, storm clouds, squall lines, that kind of thing, and heavy rain. But then as the front passes over you, obviously you feel the temperature reduce again, and the wind once again veers. It moves around another few degrees in the same direction. Then the cloud base basically gets higher. The rain gradually stops, and eventually the clouds clear as it go past. So that's the passage of a cold front. Quite a lot quicker. That can happen in just a few hours. So it's quite not uncommon to have a cold front arrive in the morning, but later on in the afternoon you're flying again, because it all goes through much more quickly. Behind the cold front it tends to be clean air, because it's rained on it quite a lot. It's washed a lot of the crud out of the air, and cold air is nice and clear. So what will often happen is post-cold frontal, if you've got very cold air and clear skies, so you get a bit of heat from the sun, you will then start to get thermal. Once the ground has a chance to warm up a little bit, you'll get warm ground and cold air, and therefore you get some thermal activity. So quite often the best cross-country days are sort of the day after a cold front has gone through. Anyway, so that's a cold front. Occluded fronts. So what's this? Well, basically it's a warm front and a cold front combined. Essentially the warm front is moving quite slowly, the cold front comes on a bit faster, and it eventually catches up. Where it reaches the point where this block of cool air reaches the far block of cool air and lifts the warm air right off the ground, we call that an occlusion, because there's still a warm sector but it's no longer in touch with the ground. So the occluded front, and this is shown on the chart because they show both the symbols for cold and warm on the same line, because that's what you've got. You've got cold lower down and warm higher up. So it kind of zips up, if you like, the front. So an occlusion. If you're unlucky and you catch it just at the point where the cold front has caught up with the warm front, you kind of get all the rain and weather from a warm front followed by the cold front stuff, which isn't great. But if you catch it when the occlusion's been there for a few days, or a bit later in the life of the depression, or closer in towards the centre, where it's been zipped up and it's been for a while, and the warm air has actually been lifted quite high of the ground and it doesn't have much moisture left, then a weak occlusion can just be a sort of, it goes cloudy for a couple of hours in the afternoon kind of thing. So it all depends on the timing with an occlusion, but that's what an occluded front is. Okay, and that's the symbol for it. Okay. Here's a plan of an occluded front. This is what I was talking about. You see, if you're just at the junction point there, you get both. If you're near the top of this diagram where the thing is, then it may have been, if it's been occluded for a while, there's going to be less weather. Okay, so that's how it looks. Okay, so stationary fronts and troughs. A stationary front, I've already touched on this, is very simple. It's basically two air masses, but they're not really moving. So it's just, what it says on the tin. A trough is marked by this just solid black line, which seems to be sort of completely unattached to anything and with no symbols on it on the pressure chart. A trough just means that there is a dip in the pressure. So it's like a little valley as opposed to a big bowl, which is a depression, simple as that. So these are the features of the surface pressure chart. Right, waving fronts. Now, sometimes you'll start with a static front or no front at all, and then you will get a warm and a cold air mass that are meeting. Now, if they actually meet head on and kind of stop, or they move one way or the other, that's one thing. But what very often happens is they're at a slight angle, or one is coming this way and the other one is over here, sort of thing. So as they go, they're sort of sliding across each other. So it's not always just a head-on movement of, as shown in the earlier illustrations. And what happens then is the front starts to bend, it starts to curve. So the cold air cuts in underneath the warm air, and the warm air climbs up over the cool air, if you follow me. The actual process for this, for starting this spinning action, is caused by the high level wind, because we've got this high level belts of winds, the jet streams at high altitude. So these air masses have got a predisposition to be turned. The actual mechanism is quite complex, and it's to do with the Coriolis effect, the spin of the Earth, but we won't get into all that now. So basically what you get is that it's a bit like putting oil on top of water or something like that. It actually swirls as it goes. So and then you start to get this depression forming. So that's how a depression forms in its simplest form. It's just one patch of air undercuts the other, and they do it in a curved path. So that is a waving front. They start straight and they start to S, and they S more and more until they turn into the depression. Okay. Characteristics of air masses. We can know a lot about what weather to expect if we know where our air has come from. So we divide up those air masses into sort of, depending what their source is. So we talk about polar maritime air, which is cold air that's come over a big ocean, or a lot of sea. So in our case in the UK, that's from the northwest. We talk about polar continental air, so it's dry air, but it's still very cold. Tropical continental air, which is obviously coming up from the equator, but it's coming off basically a landmass, and tropical maritime air, which is warm, moist air, where we get a lot of our weather from. Right, so it's important to know about what the air masses are, but it's not always quite as straightforward. The characteristics of the air mass depend on a number of things, partly on the time of year, but also on the path that it's taken to get here. So an example of this is in the winter, you might get a southeasterly wind, and you think, oh, right, southeasterly, that's tropical, continental air. It should be warm and dry, but it's not. It's cold. Why? Well, because, as mentioned earlier, air masses often go in a curve. So if you look at the arrow here illustrating, although it might be southeasterly, it may actually have started out as polar continental air, and it's just come round in a big swirl. And the same happens, you can visualize it with the other sectors. So knowing where your air mass has come from gives you a good idea about the characteristics of it. Okay, so that's basically it. That's just an introduction to big weather. It is obviously a massively complicated subject, so the difficulty is picking out the bits that are of interest, but that should give you a grounding in how the mechanism works. And we're going to build on this a little bit in another session when we're talking about micrometeorology and so forth. And there's actually a session after that on clouds, another one I'm going to do on pilot weather, pilots, lapse rates and valley winds and that kind of stuff. Anyway, I hope that's a good starter for you, and I hope you found that useful.